Hello and welcome to Real Analysis. And as always, first I really want to thank all the nice people that support this channel on Steady or PayPal. And now in today's part 32 we will talk about the intermediate value theorem. There, as before, what we will need is a continuous function f. As usual, we call the domain of the function here just by I. However, now actually we need an interval. So let's write it as AB, where A and B are included in the domain. In this case, we can draw a very nice compact picture for the graph of the function. For example, the graph could look like this, where we have the interval AB on the x-axis. And now you should see, on the y-axis, we also find an interval. In this case, we find f of A at the bottom and f of B at the top. However, of course, it could be the other way around. Now, the intermediate value theorem tells us that for all values y in this interval, we find a corresponding x. So you could say all intermediate values are hit by the function. The function simply cannot escape here if it starts here and ends there, because it's continuous and it cannot make any jumps. Therefore, the intermediate value theorem gives a meaning to the sentence that the graph of a continuous function can be drawn in one stroke. Okay, then let's formulate this nice theorem. Here I can tell you the intermediate value theorem is one of the most important theorems you learn in analysis. Now, what we have to put in, we already know. We only need two assumptions. Firstly, f should be a continuous function defined on the interval AB. And secondly, we take any number y on the y-axis in this interval. Okay, if we want to be precise, we write down both intervals, the one where we start with f of A and the other one where we start with f of B. Just depending which of the two numbers is the smaller one. For example, in our picture, we can set y through this point. And then the intermediate value theorem tells us there is a corresponding x we call x tilde. It's an element of the interval AB and it is sent to y by f. So f of x tilde is equal to y. Okay, so this is the intermediate value theorem we'll prove today. But before we do that, I present you a corollary you really should remember. It tells us that the image of the interval AB, where we denote the image with the square brackets as well, is also an interval. More concretely, it's the interval that starts with the minimum of the function f and goes to the maximum of the function f. Therefore, you see it's the same claim as before, all the intermediate values are also hit. Okay, then I would say we can start with the proof of the intermediate value theorem. In fact, as we will see, the proof is not so complicated. The first step will be to normalize the problem in some sense. In order to understand this, let's visualize the graph of a function again. This is similar as before, where now, for example, we have our y here. Now, when I say we want to normalize the problem, it means it would be nice to have this y at 0. And of course, we could just do that, so we take the whole function and shift it to 0. So simply as that, we get a new function we could call g. Now, what you should see is that the problem for searching such an x tilde stays exactly the same, but now we search for zeros. In summary, this is our idea. We simply define a new function g. And this is simply f minus the value y. Now, the next normalization we could do is that it would be nice if the value at the right is larger than the value on the left. So what we could do is just mirror the whole graph, and then we have a new function which has exactly this property. And this function we now can call f tilde. However, please note here, we only mirror the graph if it's needed. So in the formula, this would mean f tilde is defined as minus g. However, only in the case that g of A is greater than 0. If g of A is less or equal than 0, we don't have to do anything, we can just set f tilde to g. Okay, now let's summarize what we have here. First, f tilde is of course still a continuous function, and our value we search for, we could call y tilde, is just 0. Moreover, we also know that we have a minus sign or 0 on the left hand side and a plus sign or 0 on the right hand side. Therefore, the f tilde we have drawn before is the correct example we should have in mind. Okay, now the proof that will follow will look similar to the proof we already did for the Bolzano-Weierstrass theorem. Namely, we cut the interval AB in the middle and then choose one of the two intervals here. And after this bijection we will do repeatedly. In conclusion, in the end we will get a limit here. The only thing we have to do in each step is to check the value f tilde of c. If this one is greater than 0, then our c could be the new b. In other words, we would choose the left interval in this case. In the other case, we would choose the right interval. Of course, the overall idea of this definition is that we still have the same assumption, we still have the sign change from left to right. This means then that nothing really changes here, we can do the same thing again. Then of course we would define B2 and A2, then afterwards we would define B3 and A3 and so on. Therefore in the end we get two sequences out. So we have AN and BN, and by construction we know they are Cauchy sequences. Moreover, we also know that the intervals get smaller and smaller, and indeed we know that the length converges to 0. Hence, the completeness axiom and the limit theorems get us to the result that we have exactly one limit here. Now you might already know, this is exactly the point we want to call x tilde, and by construction it's an element of the interval AB. Hence the only question that remains is what happens with x tilde when we put it into the function f tilde. In order to see this, please note that the sign change for the function f tilde holds for the whole sequence AN and BN. Therefore, and by the monotonicity of the limit, we also know that this property still holds when we put the limit in front. And there you see we can use the continuity of the function f tilde and push the limit inside. Then you see it looks like this, and we can substitute this limit with x tilde. So what we get out is a number f tilde of x tilde, which is less or equal than 0 and greater or equal than 0. Hence the only possibility is that this number is exactly 0. And there you see, indeed we have solved the problem for our function f tilde. Also you should see it's not a problem at all to go back to our original function f. Because you immediately see the x tilde we found is also a 0 for the function g. This simply holds by the definition of the function f tilde as a flip when we need it. However, the function g was defined by f minus y. And because this is now 0, this implies f of x tilde is indeed y. And that's exactly what we wanted to show, so the intermediate value theorem is proven. Okay, then I would say, please remember this important theorem, and then I see you in the next video. Have a nice day and bye!